Most, if not all, of the world's electric power supply systems are widely interconnected, involving connections inside utilities' own territories, which extend to inter-utility connections and then to interregional and international connections. This is done for economic reasons, to reduce the cost of electricity and to improve reliability of power supply. As power transfers grow, the power system becomes increasingly more complex to operate, and the system can become less secure for riding through the major outages. It may lead to large power flows with inadequate control, excessive reactive power in various parts of the system, large dynamic swings between different parts of the system and bottlenecks, and thus, the full potential of transmission interconnections cannot be utilized. Bigger demands in transmission, lack of lasting planning, and the necessity to deliver open access to generating companies and consumers have shaped inclinations toward less security and reduced quality of supply. The FACS technology, or the Flexible AC Transmission System, is vital to ease these problems. FACS is an alternating current transmission system incorporating power electronic-based and other static controllers to enhance controllability and increase power transfer capability. The FACS technology opens up new probabilities for controlling power and enhancing the usable capacity of the existing as well as new and improved lines. The likelihood that current and therefore power through a line can be controlled enables a large potential of increasing capacity of the existing lines. These opportunities arise through the ability of FACS controllers to control the interrelated parameters that govern the operation of transmission systems, including series impedance, shunt impedance, current, voltage, phase angle, and damping of oscillations. The basic idea of FACS is installing the power electronic devices at the high voltage side of the power grid to make the whole system electronically controllable. The FACS technology is not a single high-power controller, but rather a collection of controllers which can be applied individually or in coordination with others to control one or more of the interrelated system parameters. There are four main types of FACS controllers. First is the series controllers. It consists of variable impedance devices like capacitors or reactors, which introduce voltage in series with the line. It reduces the inductivity of the transmission lines. Examples of the series controllers are static series synchronous compensator or SSSC and thyristor switch series capacitor or TSSC, which are widely used in asset optimization, angle stability, and transmission cost minimization. The second type is the shunt controllers. It consists of variable impedance devices like capacitors or reactors, which introduce voltage in series with the line. It reduces the capacitivity of the transmission lines. Examples of shunt controllers are static synchronous compensator or STATCOM, thyristor switch reactor or TSR, thyristor switch capacitor or TSC, and static var compensator or SVC, which are widely used in voltage control and stability, asset optimization, and transmission cost minimization. SVCs are also used in angle stability and in order to avoid congestions. The third type is the combined series controllers. These controllers consist of a combination of series controllers, with each controller providing series compensation and also the transfer of real power along the line. Example of this type of controller is interline power flow controller or IPFC, which is widely used in managing the power flow of multi-line transmission system. The fourth type is the shunt series controllers. These controllers introduce current in series using the series controllers and voltage in shunt using the shunt controllers. Example of this type of controller is the Unified Power Flow Controller or the UPFC, which is the combination of SSSC and STATCOM without any external energy source and exhibits the characteristics of both types of controllers. It is widely used in many applications like voltage control and stability, asset optimization, line overloading limiting, angle stability, transmission cost minimization, and other more. FACS devices and controllers is an enabling technology and not a one-on-one substitute for mechanical switches. You mainly find application of FACS devices in the following areas. First is power transmission, Power quality. VRE grid connection. Railway grid connection. And cable systems. Here are the notable advantages of FACS devices and controllers. As FACS can alter the impedance in the line, it increases and control of power transmission capacity in the line as ordered. The use of control of power flow may be to follow a contract, meet the utility's own needs, ensure optimum power flow, ride through emergency conditions, or a combination thereof and prevents loop flow. And in the same way, it increases the loading capability of the lines to their thermal capabilities, including short-term and seasonal limits. Second, FACS help in grid integration of renewable power generation systems, especially in the case of STATCOM, which has effective control strategies for modulation of real and reactive output power. In addition, it provides greater flexibility in seating new generation. FACS, specifically SVC, provides dynamic reactive power support, which improves HVDC converter terminal performance and also filters harmonic entering the AC systems. Improvement of the system transient stability limit by controlled shunt compensation is achieved by increasing the power transmission via increasing or maintaining the transmission line voltage at the midpoint during the accelerating swing of the disturbed machines. FACS help in the mitigation of subsynchronous resonance because this kind of resonance occurs at less than 60 Hz, which historically damaged the shaft of generators. It is also used for limiting short-circuit currents by rapidly changing from a controlled capacitive to inductive impedance. FACS also help in load compensation by management of reactive power to improve the quality of supply, especially the voltage and the power factor levels. For alleviation of voltage instability, FACS provides direct voltage support to maintain sufficient line voltage for facilitating increased power flow under heavy loads and for preventing voltage instability. In the enhancement of system damping, FACS increases the system security through damping electromechanical oscillations of power systems and machines.